Now, throughout this entire chapter, we have been working with vector fields, but there's one special kind of vector field that we encountered even before we started this chapter that has some really nice properties. So if we take a scalar function, a multivariable scalar function, so either f of xy or f of xyz, and we take the gradient of that function. So remember, that will be the vector of partial derivatives. That vector of partial derivatives is a vector field. This is a vector field. Because for every point xyz, we have a vector associated with that point. So the gradient of a scalar function is a special kind of vector field. And as it turns out, it has some really nice properties. Okay, so let's consider taking, suppose C is a piecewise smooth curve. Parameterized by R of t, where t ranges from A to B. Okay, now what we want to do is we want to consider what happens when we take the vector line integral of a gradient field over a curve C. Okay, so let's do what we normally do when we're calculating a vector line integral. We've got a parameterization, so we just plug our parameterization in to our vector field, which in this case is the gradient of f. So gradient of f evaluated along r of t, and then we take the dot product with the derivative of r of t. Okay, and we integrate that with respect to t from t equals a to t equals b, since those are the endpoints of our curve. Okay, so far there's nothing different about what we're doing here versus a normal line integral with the usual kind of vector field, with an arbitrary vector field. But as we look at this looks familiar. Recall that the derivative of f of r of t with respect to t, if we use the multivariable chain rule, we get the gradient of f at r of t dotted with r prime of t. That's exactly what we have here. Gradient of f at r of t dotted with r prime of t, which means we can swap this out. We can swap our integrand out with the derivative of f of r of t with respect to t, because they're exactly the same thing. Okay, so here we're just using the multivariable chain rule. And so when I look at this now, I'm taking the integral with respect to t of a derivative with respect to t. So I need to take the antiderivative of a derivative. By the fundamental theorem of calculus, I will just get f of r of t. Right? The derivative and the antiderivative undo each other. I'm just going to evaluate that from t equals a to t equals b. And so plug in the top limit first, then plug in the bottom limit. Okay, so I can evaluate the line integral here of over the gradient of f by taking the original function f and just evaluating it at the endpoints of the curve and subtracting them. Okay, that's pretty nice. Line integrals, they can be a little unpleasant to take, but in this special case, we could skip most of the work finding the line integral, and notice we're just taking the evaluating f at the endpoints of the curve. R of b, our curve C, R of a is the starting point, R of b is the endpoint. So it's just the f evaluated at the endpoint of the curve minus f evaluated at the starting point of the curve. Okay. This ends up being a pretty important result. We call it the fundamental theorem of line integrals. It's an extension of the fundamental theorem of calculus. Okay. And it says that if I have an integral over a gradient function, okay, if my vector field is the gradient of a function, then instead of having to do the whole line integral, I just need to evaluate f at the endpoints of the curve C. Okay. So this is just going to give me f of the endpoint of curve C minus f of the starting point of curve C. Okay. Now there's some pretty interesting consequences of this. One of the consequences is that our function here, the gradient of f, is going to be path independent. The vector field, the gradient of f, is path independent. So what does that mean, to be path independent? It means it doesn't matter the path I take to get from our starting point A to our ending point B. It doesn't matter what curve C is, it matters what the endpoints are. The line integral of f, of gradient of f, over any curve from A to B will be the same. Okay, why is that? Because when we're taking the integral here, all that matters is in the end is the endpoints. Doesn't matter about all the points in the middle. Okay, so if I have two curves, let's say I have this curve here, we'll call this one C1. Okay, starts at point A, ends at point B. And then I have another curve right here. Okay, it also starts at point A and ends at point B, but it's a totally different curve. All the points in the middle, totally different. The line integral of over curve 1, C1, is going to be equal to the line integral over C2. Because all that matters, because we are dealing with a the gradient of f. All that matters is what the function value is at the endpoints. And these two curves share the same endpoints. Okay? And so we say it is path independent. It doesn't matter which path we take to get from point A to point B. The integral will be the same. The integral will be the same as long as the endpoints are the same. Doesn't matter what path I take. Okay? As long as the endpoints are the same, the integral ends up being the same. The endpoints are all that matters for a gradient vector field. Okay? Another interesting consequence, if the curve C is a closed curve, then the line integral over curve C, over closed curve C, closed means that it loops back to itself. The starting point and the end point are the same. This will always be 0. Okay? Why is that? Well, here's point A, and I do something over here, and I come back. Point B is the same as point A. My starting point and my end point are the same. It's a closed curve, which means that my integral over curve C of gradient of f dot dr is going to be f evaluated at my endpoint minus f evaluated at my start point, but the points are the same. The start point and the end point are the same. So the function values will be the same, which means I'm subtracting two of the same value, I'm getting 0. Okay? So having our vector field be the gradient of a function leads to a lot of nice properties, a lot of nice consequences. This idea of path independence for gradient vector fields is so useful. It's a natural question to ask, how can we tell if a vector field is path independent? Okay, so let's start off with the definition here. We're going to call vector fields that are path independent a special name. A vector field F that is path independent is called a conservative vector field. So the question then is, how can we tell if a vector field is conservative? So we could actually develop a test using Stokes' theorem. Okay? So imagine we're in three-dimensional space. Now, if a vector field is path independent, that means any closed path in space, the line integral of the vector field would be 0, right? Because if we're independent of path, then this and this will give the same result, just they'll be going different directions. And so if I have a closed path, I just get 0. Okay? So for any closed path, I know that the line integral of the vector field f over that closed path is going to be 0. Okay? But using Stokes' theorem, I know that this will also be equal to the surface integral of the curl of f over any surface with this this path as the boundary of the surface. Okay, so any surface where that's the boundary of the surface by Stokes' theorem, these two are equal, right? Now, very important. This is true for any closed path in space. I've drawn one example, but if we have a conservative vector field, then this holds for any closed path in space. Okay? And by Stokes' theorem, any surface that has this closed path as its boundary, the flux of the curl of the vector field through the surface would also be equal to the circulation along the path. Okay? They'd be equal. So because it holds for any closed path and any surface with the boundary of that path, the only way that this would always be equal to 0, the only way that this will always be equal to 0 is if the curl of the vector field is 0. So this implies that the curl of the vector field must be 0. Okay? And that gives us a test to determine if a vector field is conservative. A vector field is conservative, that means it'll be path independent, if the curl of the vector field is 0. Should probably write that as a vector. Okay. Now here, this applies to any vector field. In a three-dimensional space, a three-dimensional vector field, it's curl in the usual sense. Okay. And we're looking to see if the curl vector is identically 0 for every point in space. Okay. In 2 dimensions, we'd be looking at the scalar curl. Okay. And if that's 0, then the 2-dimensional vector field is conservative. Now, if we have a conservative vector field, okay, if our vector field is conservative, if it passes this test, then it turns out the only way a vector field can be conservative is if it is a gradient vector field for some function little f. Okay? Then there exists a scalar function little f, so that our vector field is just the gradient of our scalar function. Okay? So in other words, a vector field is going to be conservative if and only if it is a gradient field. We call the scalar function f the potential function of our vector field. So what this means is if f is a potential function, for a conservative vector field big F, then if I want a line integral of f over some piecewise smooth curve C, then all I need to do is evaluate my potential function. My potential function, you know what, let me make one more thing. That means that the vector field f is the gradient of our potential function f, little f. And that means that this line integral would just be the potential function evaluated at the end point of our curve C minus the potential function at the starting point of our curve C. Where A and B are the starting and end points of curve C. Okay, so this gives us a way to tell if a vector field is conservative, if it's path independent. If it's path independent, we can use this test. Check the curl. If it's 0, path independent. If the curl is not 0, it's not path independent. And that's very important. Not every vector field is going to be path independent. Not every vector field is going to be conservative. Okay? But if it is conservative, if the curl is 0, then we can find a potential function for that field. And that makes a line integral over any path in space much easier to evaluate if we have that potential function. Let's take a look at a couple of examples here. For this one, we have a vector field f with components 2x plus y squared and 2y plus x squared. We want to determine if this vector field is conservative. And if it is conservative, then let's find the potential function. So the first thing we need to do is test if it's conservative. If the curl of the vector field is 0, then the vector field is conservative. Okay, now in this case, it is a vector field with 2 components. It's a 2-dimensional vector field. So we're going to take the scalar curl. So to do that, we're going to embed the vector field in 3 dimensions. So I'm going to take the first component of the vector field, 2x plus y squared, the second component, 2y plus x squared, and then to embed it in 3 dimensions, I just make the third component 0. Okay, so to find the curl, my first row is ijk. My second row is the vector of partial derivative operators. Partial x, partial y, partial z. The last row is the vector field itself. 2x plus y squared, 2y plus x squared, 0. Okay, so for I get 0, and then partial derivative with respect to z. There's no z's in here, so that's also 0. Okay, so I is 0. J, same thing. Derivative 0, 0. I'm taking the partial derivative with respect to z of this. Again, no z's in here, so also 0. Whenever you're finding the scalar curl, and we've talked about this, those first 2 components will always be 0. The only non-zero component is going to be that k. Okay, so I'm going to get a partial derivative of this with respect to x. Minus partial derivative of 2x plus y squared with respect to y. So I get 0, 0, and I get 2x minus 2y. And so the scalar curl of f is just the last component of this 3-dimensional curl. So the scalar curl of f is 2x minus 2y, which is not identically 0. There are x and y values that I can choose which would not be 0. Okay? Because that is not 0, that means f is not a conservative vector field. Let's try another one. Here we have a vector field f. Again, we want to test if it's conservative, so we need to check its curl. If its curl is 0, then it's conservative. Okay, so I'm going to find the scalar curl, which means I'm going to embed it in three-dimensional space. 2xy cubed, comma 3y squared x squared, comma 0. I, j, k. My partial derivative operators, partial x, partial y, partial z. 2xy cubed, 3y squared x squared, 0. We've done enough of these scalar curls that we know that the first two components will always be 0 when we take the curl of a two-dimensional vector field. Okay? So for a two-dimensional vector field, only the last component matters. So for the k component, partial derivative with respect to x of 3y squared x squared minus partial derivative with respect to y of 2xy cubed. That's 0, 0, and then I get 6 xy squared minus 6xy squared. So I get 0, 0, 0, which means the scalar curl, which is only the last component of our three-dimensional curl, the scalar curl of the two-dimensional vector field is just 0. That's what we're looking for. That means the vector field is conservative. Okay? Because it is conservative, that means so we can write our vector field f as the gradient of some other function little f, some scalar function little f. Okay? So that means that our vector field, 2xy cubed, comma 3y squared x squared, 2xy cubed, comma 3 x squared y squared. I got that right, didn't I? Yes, I did. Is equal to the gradient of f, which is the vector of partial derivatives of f. Okay? So that gives me, if I equate corresponding components, that tells me that the partial derivative of f with respect to x has to be 2xy cubed. The partial derivative of f with respect to y has to be 3x squared y squared. Okay? Now, what I want to do is I want to take this information and I want to find function f. Okay? So if the partial derivative of f with respect to x is 2xy cubed, then I should be able to find f by undoing that partial derivative, taking the integral with respect to variable x. Okay, so this implies that my function f should be the integral of 2xy cubed integrated with respect to x. So we're going to hold y fixed, treat y as a constant, integrate only with respect to variable x. Okay, so if I integrate, I get the 2 and the y cubed, they kind of come along for the ride. They're constants. But apply the power rule to x, add 1 to the power, divide by your new power. Okay, and then I have to add a constant. But this is where things get just a little tricky. When I took the integral, I was integrating with respect to x, which means I treated y as a constant. So this constant c could involve y. It's not a constant in the sense that it's only numbers. It's a constant with respect to our integration. And when we integrated, we treated y as a constant. Okay, so instead of putting a c here, this really could be some function of y. Okay, because g of y is a constant with respect to variable x. Okay, cancel the 2's. So function f must be x squared y cubed plus some unknown function with respect to y. We don't know what this is yet. We would like to know what that is. Okay? That's where this other piece of information comes in. Now I know what f is, but I also know the partial derivative of f with respect to y. So if I take the partial derivative of this with respect to variable y, it should be equal to this. Okay? And using that, I can figure out what this unknown function g is. Okay? So taking the partial derivative here, partial derivative with respect to y, treating x as a constant, I get 3x squared y squared plus derivative of g of y with respect to y. Okay, but that must also be equal to this over here. These must be equal. By equating them, I can figure out what g of y must be. Okay, so that means (3x squared y squared), this over here, must be equal to this over here. 3x squared y squared plus g, the derivative of g of y with respect to variable y. Okay, and it's pretty easy to see if I subtract 3x squared y squared both sides, that the derivative of g of y with respect to y must be 0. So if I integrate with respect to variable y, I'll get my g of y function, my original function. If I can find that, then I'll have function f, my potential function. Integral of 0 is just a constant. And in this case, it is just a true constant, okay? I am integrating only with respect to y, but I know the function only involves y. So this constant does not involve x. Okay? And so my potential function here is f of xy equals, let's put together what we have, x squared y cubed plus g of y. X squared y cubed plus g of y, which is just a constant. Okay, that is the potential function. Notice that we do get a constant of integration here. So we say a potential function. Really, we should say potential functions. We get a family of functions. Generally, a potential function isn't unique. It is unique only up to a constant. You will always get a plus c once you find your potential function. Okay? That c could be anything. So if I choose c equal to 0, for example, usually the easiest choice, f of xy equals x squared y cubed, that is a potential function to our vector field. Okay? Now with this potential function, the problem doesn't ask for this, but we can easily find any line integral over our vector field. Okay? So for example, the vector line integral of vector field f over a curve C from, let's say, the point 2, 0 to the point 5, -3 is, so we want the integral over curve C of vector field f dot dr. Notice I haven't really specified what curve C is, right? Just from one point to another point. We don't really know what's happening in between. But because our vector field is conservative, it's path independent. It doesn't matter what's happening in between. Only the starting point and the ending point matter. Okay? This vector field f, our vector field f, is the gradient of our potential function. Okay? Any of these potential functions, for any choice of c, it would be the gradient of that. Because when we take the gradient, the constant will just go away, right? Constant goes to 0 when we take the derivative. And so because we can write it as the gradient of f, it's just going to be f evaluated at the end point minus f evaluated at the start point. Okay, so that would be our potential function. Again, we could choose any value of c, so you could pick 0. Okay, so x squared y cubed, I get x squared times y cubed minus x squared times y cubed. Just plugging in the x and y values into our potential function. Okay. Notice if we did add some constant here, then I'd get a plus c here, but I'd be subtracting it over here. So that's why it doesn't matter what that c is. Okay, and so this integral is just going to be, what, 25 times 27, negative 27, minus 0. So it's negative 25 times 27, whatever that is. Okay? Let's take a look at one more example. We have a vector field here. This is a three-dimensional vector field. We have 3 components. And we want to do several things with this vector field. First, we want to determine if the vector field is conservative. Is it path independent? Now, if it is conservative, then that means we can find a potential function. So we need to find it. Okay? Then we want to use that potential function to evaluate a couple of integrals. All right, so first things first, let's start with A. Is the vector field conservative? Actually, let me just copy this so we kind of keep track of where we're at. Is the vector field conservative? So we can test if a vector field is conservative by taking its curl. If the curl is 0, then the vector field is conservative. So our function here is 4yz, 4yz, comma, 4xz plus 1, comma, 4xy plus 2z. Okay. So I need to take the curl of this. So the curl of f is going to be ijk, the determinant of the matrix. First row is ijk. Second row is, you got your partial derivatives, your partial derivative operators rather. The third row, you have the components of our vector field f. So 4yz, 4xz plus 1, 4xy plus 2z. Okay, this is a three-dimensional vector field, so we expect our answer to be a vector. The first 2 components will not be 0, unlike a scalar curl, okay, over a 2-dimensional vector field. Okay, so for the I component, partial derivative here with respect to y, I just get, what, 4x? Minus this partial derivative this with respect to z, I get also 4x. Okay, so good start. That first component will be 0. In order for this to be conservative, I need all the components to be 0. All right, so j component. Partial derivative this with respect to x, I get 4y. And then partial derivative this with respect to z, I also get 4y. So far, so good. This will also be 0. Okay. Finally, k component, partial derivative with respect to x of this, I get 4z minus partial derivative of this with respect to y, I also get 4z. So 4z minus 4z. I do get 0, 0, 0, the 0 vector. Because the curl is 0, that means the vector field is conservative. Okay, so part A is done. We have determined that f is a conservative vector field. Now, since it's conservative, that means it has a potential function. Let's find that potential function. Okay, the potential function of our vector field f, it means the gradient of our potential function, little f, is going to be equal to our vector field, big F. So the gradient of our potential function, that'll be partial derivative of f with respect to x, with respect to y, and with respect to z. I'm in three-dimensional space, so I have a three-component vector. And our vector field f, big F, was, what was it again? There we go. 4yz, 4xz plus 1, 4xy plus 2z. So if I equate corresponding components, my partial derivative with respect to x will be 4yz. Just equating first component with first component. Second component with second component. Partial derivative of f with respect to y is 4xz plus 1. And partial derivative of f with respect to z is going to be 4xy plus 2z. Okay, so I have the partial derivatives of f, but I want to find the potential function f itself. So I need to undifferentiate these. This is the derivative with respect to x. I need to undifferentiate it with respect to x. Notice it doesn't matter which one I start with. I could take the derivative of this with respect to x. I'm sorry, the antiderivative of this with respect to x, or the antiderivative of this with respect to y, or the antiderivative of this with respect to z. I have a choice. Because I have a choice, maybe pick the one that's going to be easiest. Okay, maybe I'll pick this one. So, since the partial derivative of f with respect to x is 4yz, f itself is going to be the antiderivative of 4yz with respect to variable x. And that's just going to be 4xyz plus a constant, right? But here we're treating anything that's not x as a constant, specifically yz. So that plus a constant, it could be a function of those two variables, y and z. Okay? So in order to find f, we've made some progress. We know it's equal to 4xyz plus some function involving y and z. Okay? But in order to nail it down, we need to figure out what this function is. All right? So what I'm going to do is I'm going to take the derivative either with respect to y or with respect to z. Again, we have a choice here, but I need to use some of this other information I have. Okay? In this case, let's take the partial derivative of f with respect to y. So taking the partial derivative of f with respect to y based on what I have, partial derivative of 4xyz with respect to y is going to be 4xz. And partial derivative of this function with respect to y, well, it's the partial derivative of that function with respect to y. That's what I'm trying to figure out, is that function. Okay? So what I'm going to do is I'm going to equate these together. So 4xz plus 1 must be the same as 4xz plus the partial derivative of g with respect to y. If I subtract 4xz from both sides, I get 1 equals the partial derivative of g with respect to y. I want to find g itself, so I need to integrate. So integrate both sides with respect to y to undo the partial derivative with respect to y. That gets me back to my function g of yz. That's what I want to know. The integral of 1 with respect to y is just going to be y plus a constant. Here's where things get a little tricky again, right? I'm treating only y as my variable. Any other variable I'm treating as a constant. So when I say plus a constant, that constant could involve other variables. Now, it cannot involve x. Because this function g of yz, it involves only variables y and z. So x is out. I cannot involve x. But I'm treating z as a constant in this integral. So when I add that plus c, that constant could involve variable z. Okay? So it could be some function of z. So we know a little bit more about g of yz, but don't quite have the full picture, right? Because we don't know what this is going to be. So what we need to do is we need to plug this back into function f up here. So let's take this, pull it up here, plug it in. What do we get? We have our f is equal to 4xyz plus g of yz. But we now know a little bit more about that g of yz. It must be y plus 4 plus h of z. So plus y plus h of z. I still need to find that h of z for my final answer, for my final potential function. Okay? So I've used the partial derivative of f with respect to x. I've used the partial derivative of f with respect to y. Let's use the other piece of information we have, the partial derivative of f with respect to z. So I'm going to take the derivative of this, my most updated version of function f, of my potential function. I'm going to take the partial derivative of it with respect to variable z, and then I will equate that with this, which I also know is the partial derivative of f with respect to z. Okay, so partial derivative of f with respect to z, I get 4xy. Derivative of y with respect to z is 0. And then the derivative of h with respect to variable z. Okay? And so let's pull this guy down here. Let's pull this guy down here. Let's equate them. Give a little bit more space between that and our previous work. 4xy plus 2z is what we know from over here, what the partial derivative of f with respect to z is, but we also know it's 4xy plus the derivative of h with respect to z. 4xy plus the derivative of h of z with respect to variable z. So I'm trying to find what this function is. So let's solve for it, cancel the 4xy. 2z equals the derivative of h of z with respect to z. I want h, not h of z, so let's integrate with respect to z on both sides. Okay, on the right-hand side, I'm taking the integral of a derivative, so it just cancels out. I just get h of z. On the right-hand side, integral of 2z is going to be 2z squared over 2, or just z squared, right? Plus a constant. But finally, this function is just a function of z. So the only thing that this constant could just be constant numbers. Okay, it's a constant number. The function cannot involve x or y because we've already ruled this out. It's just a function of z. So this plus c really is a plus c this time. And so if I plug that in, I'll get my final answer. So let me pull it down here. So function f, let me go a little lower. There we go. Function f, my potential function f is going to be 4xyz plus y plus h of z. So 4xyz plus y plus h of z, where my h of z is z squared plus c. Okay. Again, we call it a potential function, but really it's a family of potential functions, right? It's only unique up to a constant. Any choice of c would be a potential function for our vector field. Usually we just choose c then equal to 0 to make it as simple as possible. Okay? Okay. So that's part B, done. We have our potential function. Now let's use that potential function to evaluate a couple line integrals. So part C, we want to use our potential function we just found to evaluate the line integral of our conservative vector field along a smooth curve from 510 to 312. Okay? So because it's conservative, my vector field f is just the gradient of my potential function little f. And by the fundamental theorem of line integrals, that's just going to be our potential function evaluated at our end point, we end at 312, minus the potential function evaluated at the start point, 510. Again, since it's a conservative vector field, it's path independent. So the only thing that matters is the starting and end point. Any path in between, the line integral over that path will be the same. Okay, so we have our potential function. Let's plug in. So it was 4xyz plus y plus z squared. Plus z squared. And then plus c, but any choice of a constant c would work. So I'll choose 0. Just leave it off. Okay. Minus, now same thing, but plug in the second point. 4 times x times y times z plus y plus z squared. And I get over here 4 times 3 is 12 times 1 times 2, that's 24 plus 1 plus 4 minus over here I get a 0 in that product, so that's 0 plus 1 plus 0. So I get 24 plus 1 plus 4 minus 1, that's going to be 28. All said and done. So once you find the potential function, finding a line integral over any path becomes almost trivially easy. You just plug in the endpoints of the line into your potential function. Okay? Okay, and we have one more question. There we go. We want to use that potential function one more time, this time to evaluate a line integral over a closed curve C. So just as before, that vector field, f, is the gradient of our potential function. And so we can calculate the line integral by calculating f of our endpoint minus potential function evaluated at our start point. Okay? But all we know here is C is a closed, smooth curve. Well, if it's closed, then hey, that's our start point right here. And then, you know, maybe our curve does something. Ooh. But then, because it's closed, the endpoint is the exact same point. So f of end and f of start, the start point and the end point, the function values will be the same because the start and the end point is the same. I'm plugging the same thing in. We've seen this earlier when we were talking about conservative vector fields. But the line integral of a conservative vector field over any closed curve will always be 0 because the endpoint and the start point are always the same for a closed curve.